And this is my introduction here, which is Asteroid Bennu, which is what we were able to collect a sample of last, I guess it was 2 years ago now, I apologize, October 2020. The pandemic's made all of the time kind of feel squishy. And so I'm going to talk a little bit about the mission as well as some of the near-Earth object missions that we have going on and upcoming. And then I'm going to give a little bit of background about myself, because as Stacy said, I'm a mission manager, and that's kind of a unique title. And I was never one of the people who knew what I wanted to do when I grew up. And I'm still not sure I want to know what I'm going to do when I grow up. So I love learning new things and trying new things. And so I got my start for my career by cookies. I love everything about cookies. Eating cookies, baking cookies, sampling cookies, tasting cookies, any of it. And when I was growing up, I used to bake cookies with my grandmother. My grandmother came from Sweden, and she would measure by pouring things into her hand in a pile or using a coffee cup and just kind of dumping ingredients together. And I found that when we would do that, and I would have a little bit bigger pile of salt in my hand, or the butter wasn't soft, or we had to substitute a different type of fat, that the cookies came out differently. They were crispy, or they were chewy, or they were a little bit puffy. And so that got me thinking, well, this is really neat. So as I started doing some research on it, I found out that that was actually chemistry. And I loved it. I love edible chemistry, my favorite kind of chemistry. And I started enjoying the process of how different order of things, different processes of how you put chemicals together, ingredients in a cookie or any other type of chemical, how that can change it. And so that's actually called chemical engineering, which is what I have my undergraduate degree in from the University of Toledo. And so when I graduated, I wanted to try my hand at jets. I grew up next to an Air Force base. I loved learning about jets and jet fuel and the way it broke down in the engine and how it decomposed and what kind of, deposits it made, what that did to the engine, as well as, the emissions and the plume side of it. And so I spent some time working for the Air Force, developing some different alternative fuels. We would, make fuels and then burn them to see how they decompose. I developed some different test rigs to look at that decomposition, and it was fascinating to me. And so moving forward in my career, the next question I had was, well, what's all the stuff coming out the backside and how does that affect our environment? So I went to go work at the Environmental Protection Agency, and I worked on the Greenhouse Gas Initiative, and I worked on developing marine ocean-going vessel fuels to make sure they're cleaner as they come within our borders, as well as aircraft emissions and how we can regulate those to make sure that they're cleaner. And in working with the aircraft fuels and the aircraft emissions, I got very interested in space fuels and aerospace fuels. So the next logical step in my career was going to do space vehicles. So I worked as a lead systems engineer for the space launch system that will be launching later this year. I worked on the ICPS, which is the middle stage, the upper stage that connects Orion, which is what the astronauts will go in, to the rest of the rocket. And I worked on some of those interfaces, and I learned a lot about different, space things, right? Different trajectories, different environments. There's a lot of shaking when you do a rocket launch, a lot of different vibrations, a lot of different parameters that you have to look at that are different from, say, a car or a plane or an ocean-going vessel. So I found that fascinating. And so the next step in my career was to work for NASA directly and to work with some of those space missions that have launched up and do some of this really cool space science. And so that's what I do as a mission manager. I use some of my regulatory knowledge, I use my budgeting, I use my science background and my engineering process background, and I kind of put those all together to help make sure that the missions run smoothly. And there's a huge team that we work with. We have, program engineers and program executives at the headquarters level. We have program scientists at the headquarters level at NASA. We have the, primary investigators on the missions who work with us, and they have a whole team of amazing scientists and finance people and just artists. And you'll see a lot of the neat graphics that we've put together as the OSIRIS-REx team through this presentation. And so that's kind of a little bit about my background and how I ended up interested in science to begin with, chemistry, chemical engineering, and how I ended up at NASA as a mission manager. And so at NASA, we have a lot of space missions within the Space Mission Directorate. You'll see some of these here. Psyche is going to launch this summer. And so you'll see some of these missions flying up here, and some of them you may remember. Some of them are older. Some of them have been around for a while, and some of them have recently launched. Da Vinci is going to be coming up in a few years. That's a new mission. Near Earth Object Surveyor, I'm going to talk a little bit about at the end. Europa Clipper is going to launch in the next year or so. And so at NASA, we have a lot of different science missions that look at different mission goals. And as a mission manager, it's our job to work with the headquarters team as well as the science team that proposed this mission, because NASA does missions by proposal. And that's kind of how we move forward with those. And so I'll talk a little bit about this mission right here. The Origins Spectral Interpretation Resource Identification Security Regolith Explorer, which is the biggest mouthful mission that I have ever seen. So we nicknamed it OSIRIS-REx. So why do we call it OSIRIS-REx? Well, the team used the goals of the mission to create an acronym for the spacecraft. So the O, the origins, is to return and analyze a sample of a pristine asteroid, a carbon-rich asteroid, to kind of tell us a little bit about how it formed, to give us an idea of maybe how Earth formed or what Earth was like years ago, based on the minerals and the organic material that we're hoping to bring back from our sample. Spectral interpretation and resource identification, the SI and the RI, also really big words. We are hoping to define the properties of Bennu, of a carbon-rich asteroid, so that we can compare it to the data that we've collected on ground-based telescopes. We have a lot of data that we've collected from the ground and from some space telescopes, but to have that sample and be able to compare the data to say, hey, wow, we were right, or hey, wow, we were way off. It's very, very informative in the scientific community to do that, and that will tell us a lot about other asteroids in our area, in our near-Earth objects in our area. And also to the resource identification, to map the properties of the asteroid, the chemistry, the mineralogy, like what's there? Does it have geologic and dynamic history? Can we figure that out? And to give some context to the sample, because we're going to have a lot of images and a lot of information from the sample site. So that will tell us a little bit more about the sample when we have it in hand. The S for OSIRIS-REx, or the second S, is for security, to measure something called the Yarkovsky effect. So the Yarkovsky effect is actually where energy from the sun comes and hits a celestial body, and then as that body is rotating, it can take that energy and kind of give it a little bit of a push. And so depending on which way that celestial body is moving, it will either come closer to Earth or farther to Earth. And so Yarkovsky effect is what the name of that effect is. And so we measure that to see, as Bennu is coming closer to Earth, how much effect of how much is the Yarkovsky effect impacting that? And so we use a lot of the data we collected to look at that. And the Rex is for Regolith Explorer. So regolith is the surface of the celestial body. So the surface of Bennu is covered in regolith, the rocks and the dust and the other surface structure that it has, the sandy surface we thought it had, is regolith. And so the Explorer is that we're actually going to document the texture and the chemistry and the other properties of the surface up there while we are orbiting the asteroid, as well as on our sample as we bring it back home. And so the OSIRIS-REx spacecraft launched in 2016 in September on an Atlas V by ULA. And you can see one of our extra mission patches there in the center. And then just to give you an overview of the spacecraft, I've told you a little bit about why we named it what we named it based on the goals of the mission. But the spacecraft itself, it's actually not very big. It's only about 20 feet with its solar panels deployed. It has solar panels that deploy, and you can see in some of these images, and you can see next to the average size people, that it's not a very large spacecraft. It's about 10 feet by 8 feet when its solar panels are not deployed. We also have an arm on it. It's called the tag SAM arm, or sample arm, and it's 11 feet long, and you can see that in the center picture there. And the sample head that we have on it, it's about the size of a dinner plate. And what that does, we designed that to impact the surface, and it has some mylar flaps on it. And we have nitrogen bottles that we evacuated to swirl some of the material back up into the sample head. And I have a cartoon of that here. So you can see where the sample head would hit the surface, and we would swirl nitrogen bottles, and it would collect material. The sandy surface is what we thought Bennu had, and it would collect it over into the sample head. And then the sample head would sever and come back on the spacecraft and come back to us. And the bottom left picture that you can still see, the bottom picture is actually an image of OSIRIS-REx as it's separating from its launch vehicle. And so that kind of tells you a little bit about the OSIRIS-REx vehicle. So why did we choose Bennu, and how did we name it? So there are a lot of asteroids out there, and we wanted to get one that we wanted to sample an asteroid in a short period of time. We didn't want to have to travel a very far distance. We wanted a near-Earth asteroid. So that brought it down to just over 7,000 choices of near-Earth asteroids. And we also wanted an asteroid, a carbon-rich asteroid, and an asteroid that was a large enough diameter that we could actually orbit it. If it was too small, it would spin too fast, and we would have some problems with the gravitational pull of a safe orbit of the spacecraft. So it had to be large enough that we could orbit it safely. And as I said, carbon rich. And so when you start putting all these together, you end up, you can see the pyramid over on the side. We ended up as Bennu as our top choice because of all these criteria we had to meet. And Bennu is not a very large asteroid. It's a little bit wider than the Empire State Building. You can see that in the little pictorial there. And it spins, it's got about 4.5 hour rotation where it spins, and it comes close to Earth every 6-ish years. And so it has kind of an, an ovalish type orbit around Earth. And the asteroid actually was named Bennu as a competition, a national competition that they put forth, and I think it was a 6th grader, a young child, a student, put the name Bennu forth because Bennu is depicted as a heron in ancient Egyptian mythology, and that it's a rebirth and looking forward, as well as Osiris being the god of the underworld and kind of the twofold of that. The description is that when the OSIRIS-REx was coming for its touch and go, it puts its solar panels up in a safe trajectory. You'll see that in a safe or a safe location. And then it has its sample arm that comes down, and it looks kind of bird-like when it does that. A lot of the names of features on Bennu are also birds to stay with the bird theme of the heron. So as I said, we launched in September of 2016. And this is our first image of Bennu. And this is how we got there. We used our star trackers, which looks for our object, right, our Bennu, and started setting a course for it. And this was taken 4 days after we launched. And so then we had some additional images. So it took us 2 years from that first grainy image you just saw to this one. And within a matter of days, as we got closer and closer to Bennu, we were getting better resolution images coming back, and we were able to kind of see the surface more clearly. And this was, I said, this was about 2 years after we originally launched. And so this will show us as a little video clip what it looks like as we got closer to Bennu. And from all the ground-based data we had at the time, the IR signature of Bennu told us that it was a very sandy surface. So we had instrument LiDAR to kind of just scan the surface, the sandy surface. We were just going to come in. We could really take a sample anywhere. We thought we had a huge area. We were very unconcerned with that part of it. And as we got closer and closer to Bennu, and you guys can probably see this yourself, it doesn't really look sandy. As we got closer and closer to it, we realized that it's actually a very rocky surface. And so, thinking about it, sandy and rocky, they're not the same. So we were very torn as to what we should do in that situation then. What we had designed for is not the situation we arrived at. Bennu seems to throw us a curve. So we decided, okay, we're just going to collect data. As a scientist, first thing you do, you collect all the data you can. So we started imaging and using all the instruments that we talked about earlier to look at the surface of Bennu and to start taking pictures and to start looking at the surface chemistry of it and to start understanding it. And what we found is that Bennu's surface seemed to have just a lot of very large boulders all over it. And those boulders could very easily harm our spacecraft as we came down to collect a sample. So then we're stuck with a problem of, well, now what should we do? Well, we had to pick a site. We had to pick the best site, a site that was going to be very safe for our spacecraft, so it wouldn't have any kind of damage to it. It could collect the sample properly, stow the sample, and come back to Earth without any damage. We also wanted a very scientific sample. We wanted a sample that was diverse and had as much different material as we could find. And so we selected 4 sites. It took about a year where we circled around the asteroid after we got there in 2018, and we looked at each of these different sites at high elevations and at closer elevations. And we decided from all of that data that sample site Osprey was probably going to be the safest bet. However, sample site Nightingale, while it may not be inherently as safe as Osprey, had a lot more potential for different types of material. And you can see that it has a lot of different colors, the darker and the lighter, that tell you that there's a lot of different types of materials in this sample versus some of the other. So this then created its own problem, because as you can see, there are a lot of really large rock formations on the surface here at this sample site. So we were going to have to fit our spacecraft down in between all of these rocks without damaging it, and also come back up with our sample without damaging the spacecraft. So we went from having this big, huge area that we thought we would have to a very small circle. And within that circle, there were even some boulders and some larger rocks we had to watch for. So the next step we asked ourselves was, well, how are we going to do that? We did that by developing something called natural feature tracking. So what we did is we just imaged the Nightingale site from a very high altitude to a very low altitude, all the way down. We did 3 runs. And so we took all sorts of images. We then put those images into a catalog, and we wrote a code for the spacecraft to use that catalog to mark where it's coming down, so that the spacecraft could autonomously come down and come to the surface. And if it had a feature that was out of space, or if it was off on its trajectory a little bit, it would just instantly back up and we could try again. And so we made a hazard map of safe areas and unsafe areas. And so this was how we ended up developing a way to actually come down and sample in between all the rocks. And we also did this for the Osprey site as well as our backup site. So we wanted to test to make sure that this was actually going to happen. So this is actual video that OSIRIS-REx took of our checkpoint rehearsal in April of 2020. This was our first activity we conducted in the pandemic. It was shortly after the pandemic started. We had a lot of obstacles to overcome in the beginning of the pandemic, as I'm sure everybody did. And in this video, you can see how the spacecraft kind of comes down, and we're going to slew away from the asteroid. And then we're going to come back in, and you will see the surface of Bennu come up, and you will see the Nightingale site here come up shortly as we come up on it, and it gets a little bit closer, and then we back away. So we went at about, I think it was 140 meters from the surface for this checkpoint. We did it again a little bit closer in August. So we took the data we had in April and we said, yeah, we think we were pretty close to our target. We think that the natural feature tracking worked really well. We did it again in August. We called it match point rehearsal. That one also went very, very well. So we felt that we were ready as a team. And in October 2020, we actually conducted our tag. And this is images that we have stitched together to make a video of it. And you can see the impact right there where we actually impacted the asteroid. And you can see we made a big impact. And so just watching this, I get goosebumps every time I watch this still. We were able to do even just some video early collection analysis from this. You can see the top of the head at the 12 o'clock spot, how some of the material kind of pushes up and some of that's moving. And you can see that the head is starting to kind of go down into the surface of the asteroid. And as it pushes further, it actually went in 19 centimeters into the surface of the asteroid. And you can see regolith material flying everywhere. So we definitely made contact with the asteroid. We are positive of that. So the next step that we had was, how do we know if we have enough material to come home? Did we collect all the material we wanted to collect? And we had two ways planned to do this check. The first one was a visual check. We had an image of our sample head. Remember the cutout in the beginning where it had the nitrogen that swirled? And you can see on the before tag site, it's on the right-hand side on my screen, but you can see there's some shadows coming through. You can see through the side of it. You can see it's very clean. If you look on the after tag side, you can see that there's no light passing through the side of it anymore. It's opaque, and there's some big shadows on the back side. So that told us that, yeah, we definitely have a lot of material in there. So the other way that we were going to check this is we had done some mass measurements of the spacecraft, where we extended the sample arm out and we spun around and we took a measurement. And then we were going to do the same thing with the full sample head to see how much mass we thought we had. Except when we started looking at some of the images and stitching them together in a video, we saw this. And so you can see regolith material coming out of our sample head. Our sample head is packed so full that we were losing material. And our fear was that if we spun it around to do that mass measurement, we were just going to fling all that material out. All that hard gained material would just fly out. And we didn't want to risk that. So we met with the science team, we met with the NASA headquarters team, and we decided that we were confident we had collected a lot of material, enough to meet our requirement to come home. And so at that point, we said, we're going to stop doing that. We're not going to do that mass measurement where we move our arm. We are going to stow, put our sample head back into its storage container to come home, and we're going to sever the arm. This is a cartoon of how that would go down, how that did go down. As the head comes in, it locks and it kind of wiggles to make sure it's locked in place with those brackets. And then this is actually video of our sample head being encapsulated for its journey home. So this was a very exciting day for us. And so the next question we had to ask ourselves was, well, we saw all that material flying. What did we do to the surface of Bennu with our tag attempt? What happened to it? So we ended up doing another flyby and looking at images of Bennu after tag to see what had happened. And you can see from this is, before tag and then after tag. And you can see how that circled boulder, that circled rock, regolith material has launched outside of it. And you can see where that X is. That was our impact crater. So we definitely left our mark on Bennu. And it was very neat to come back and see this and to see kind of the changes that happened from our tag. However, it was also very interesting and exciting to our team because they also were able to take pictures of Bennu again. And so we had almost 2 years in between the original images we took for our natural feature tracking, as well as the images we took after tag. So we took the original ones in 2019 in the January-February timeframe, and the second ones we took January-February timeframe in 2021. We were able to see changes in the asteroid itself from those images that we would not have been able to see if we hadn't gone back to look for our crater. So that was pretty exciting to us as well. And so what comes next for OSIRIS-REx? And I have a short video clip that I'm going to play because it's a very well done animation. If there's problems, I'm sure Stacy will please tell me if it's not playing right, but I'm going to come back and talk after this, but I thought this was a really neat thing to end with for the OSIRIS-REx portion.
OSIRIS-REx approaches Earth. It will jettison the sample return capsule that contains pieces from asteroid Bennu. The SRC will then travel through Earth's atmosphere and land under parachutes at the Utah Test and Training Range on September 24th, 2023. Once recovered, the capsule will be transported to the curation facility at NASA's Johnson Space Center, where the sample will be removed for distribution to laboratories worldwide, enabling scientists to study the formation of our solar system and Earth as a habitable planet.
So we are preparing right now for that sample to come back. We are getting our clean rooms ready at NASA Johnson. We are making sure we have all the agreements and the plans in place for how we're going to open that. We've done some practice runs with mock-ups where we know how to open it in a safe, clean environment, just in case it's got material all over it, because we saw that material flying. So we don't know what it's going to have on it, if it will still have it after reentry or not. So we're trying to anticipate every scenario and plan for it. So we will be prepared next fall when the sample comes back. And so I've talked a lot about OSIRIS-REx and Bennu being a near-Earth object. But what exactly is a near-Earth object? And why do we care? Why are these important to us? And so, they're important to us because they are kind of in our Earth's neighborhood. Anything within about 145-ish kilometers outside of Earth is considered a near-Earth object. And these are comets or asteroids or other small pieces of a celestial body that have been kind of pulled by Earth's gravitational pull or nudged by other gravitational pulls in the solar system, the sun, or other planets. And sometimes we'll see these as they come through. We'll have, meteor showers that we can see, or we'll have comets that we see. If you remember in 2020, we had comet Neowise. And that was something that was that was found by the Neowise telescope. And there's a picture here of it over Stonehenge, because I just think this is an amazing picture. And I've got the image copyright here. And there's the gentleman that took this. I was very impressed with it. But the Neowise comet was so bright that you could see it with a camera or a telescope or binoculars. And so that's a very rare, unique thing. A lot of near-Earth objects burn up as they come through our atmosphere, if they even come close to Earth at all. And so one of the reasons, why we want to know about these is so we kind of understand, because they are in our neighborhood. We want to know, are they coming near us? Are they not? Are they going to go past us? Do we have to worry? Because we do know there can be terrible things if a large near-Earth object would hit Earth. It happens very, very infrequently for a large one, but it has happened in the past, and we have seen craters. Crater National Park is one. There's some up in, there's one in, I think it's in the glaciers up in the Scandinavian area that they've recently found, as well as some in Australia. And so trying to understand and being able to identify these near-Earth objects is a very important thing for us as Earthlings. And so how do we do this, and how can we find them? Because a lot of these near-Earth objects are dark, because the only light in space is the sun. And so a darker space body, a darker asteroid, is going to reflect less light than a light asteroid or a high albedo asteroid, right? And if we look at the visible light spectrum, they could be the same size, but their color, if they're a darker asteroid versus a lighter asteroid, that can throw off our sizing of it, because a brighter asteroid will reflect off a lot more light and look bigger than a darker asteroid. And so if we use an infrared light band, that kind of tells us it can see all the different colors kind of evenly. A low albedo asteroid, and a high albedo asteroid show up in the infrared band about the same size. And you know how I said how the lighter ones in visible light can look brighter? Well, that means that you could have a very small, you know, high albedo asteroid, and it would look the same. It's much brighter, so it would look the same as a very large, you know, darker asteroid. And so your sizes, if you're using the visible light, would be thrown off by that. But if you use the infrared light, they're pretty, you can tell based on size because your brightness corresponds to your size of your asteroid or your celestial body, not just the brightness. And so this is how we use technology for telescopes to find some of these near-Earth objects. And so NEO-WISE is an infrared telescope out there right now. It was launched in 2009. This is the telescope that saw the comet from 2020. And it looks at, you know, the whole sky. It kind of has this wide field. And it can't see a lot of things, but it does see a fair amount. And so one of the thoughts is in the NASA planning is, well, what would the next generation look like? And the next generation would look like NEO Surveyor. And I apologize. These are some of the images that NEO-WISE has taken of space. So not necessarily near Earth objects as they come near us, but some that are within space as near Earth objects as well as a little bit further out. And I'm just going to kind of flip through these because I think they're just really beautiful. The Andromeda Galaxy. Here you can see this from WISE. Very cool. The Unicorn's Rose, it's a Rosette Nebula, which I thought was just, it's just a beautiful image. And if you go and Google NEO-WISE and NEO-WISE images, you can find a lot of the images that are out there. It's all out there for public use. And a runaway star plowing through space dust is just, I mean, that's just a really cool image. And so this, the different, the blue circles you can see here, the data that we collect from that tells us about those celestial bodies. And we can use that data to figure out what they are, where they're traveling. And it's a really neat thing that we were able to do that. And so as I said earlier, you know, the next generation is NEO Surveyor. And this is going to be another, you know, infrared telescope. And it just is going to have a little bit broader of a field, a little bit bigger. And it's just basically going to scan the sky. That's all it's going to do. It's just going to survey back and forth and just put out a ton of data. And it's going to let us be able to identify any asteroid, comet, any kind of near Earth object within about 30 million miles of Earth. This mission, this telescope is expected to launch in the spring of 2026. And so this is currently in phase B. So we're currently working on this mission and developing a lot of the designs of the telescope and the different systems that have to go into something that sits up in space and has to be passively cooled. So with that, I think I have finished my presentation.